Hilbert was the greatest mathematician, perhaps, of the beginning of 20th century. And he was a good lecturer. He said, you always have to say it 3 times. Always say it 3 times. The most important thing in dynamics, what symmetry is, I'll define it 3 times. 1. Group G is a symmetry if for every solution f of x. Remember what this f is. It's a map. You had some velocity field, you integrated it for time t. So that's a solution of your equations of motion. For every f of x and every element of the group f of g of x. What I mean by this is, if I figure out that if I go on a line between center to center and this bounce here going up that way and returning in 2 reflections is a solution, then by symmetry, for example, if I flip it, so a solution. If I apply the symmetry, this is also a solution. Sigma times f of 2 bounces, or and actually any place on this trajectory is a solution. So that means that if I have a symmetry, I only have to compute this solution once, and symmetry will take care of all of its copies. So that's one way to say it. 2. A dynamical system, which means a state space and a law of motion, is equivariant, G equivariant, meaning under the action of the group G. If action of the group, if G for every element commutes with the action of the time evolution, dynamics in time, F, meaning that if I take my coordinate and then I apply my evolution law, I get the same result as starting at a coordinate and then applying evolution law. Happy? Then there's the way that physicists tend to think about it. The law of motion is the same in all frames. And now I use this definition of changing the frame, but now the M will be an element of the group of symmetries. So it says that if I start at X, apply my group, so symmetry, evolve myself with my law of motion time t, and then go back by using the inverse of the group. I guess it's just matrix multiplication, so I can do it that way. And time is implicit. The law hasn't changed. So, well, in general, a non-singular matrix could be worth thing. You could take your cube and you can deform it and God knows what by a nonlinear transformation. And then in new coordinates, they all look very weird. If the symmetry, if G is the element of the symmetry group, then no matter how I write my Newton's laws, they have the same form. Yeah, they're identical condition. There are 3 ways of stating it. One way says, I first change coordinates, apply my motion. So it means full statement. That happens almost never. When they commute, you have a symmetry. That's almost the definition of a symmetry. So that's one way to do it. The physicist's way to do it is to say that if I compute this guy, I can just map it into this coordinate and it'll give me the other solution. So it doesn't matter where I'm going from 1 to 3 or from 2 to 3. I get the same solution. And the first definition was that if I found one solution, then symmetries give me all copies of it. So all of them, they're the same statement. Depends how you like to remember. So the funny thing is, in this subject, because you have such good intuition about playing pinball. It's actually easier to explain the subject in a more complicated setting in two-dimensional plane than as one-dimensional problem map of the interval. So let me write the second example. I'll use the two-dimensional example. This is actually enough to describe, things in arbitrary dimensions. So if you understand this, you'll also understand how you deal with the flow on the plate that has a symmetry like that, even though that's in infinite many dimensions. So the matrix is working is here in 4 dimensions, and you figure out stability is a 2-dimensional matrices if you do it intelligently. And the symmetry will work for all that stuff, no matter how you do it. But if you're in zillion dimensions, still the symmetry might work. So, for example, I have some Fourier series. The symmetry might mean that every odd coefficient is flip. That's called a representation. So group can have representations of any dimension, meaning that it can act on any dimensional dynamical system. So here is a one-dimensional example. Let's take a unit interval from -1 to 2 to +1. Dimension of your state space is d equals 1. So if I measure where I'm on a line, I just measure one coordinate. Let's call it x. And then my law of motion, in this case I can draw the law of motion in the plane because it'll give me what happens as I apply my map in one iteration. This I'll call xn plus 1, and that's just my dynamical law applied to previous state. So these are two one-dimensional things. I can plot it as a picture, and this is last time.